Welcome learners. I am Dr. T. Gangaram, lecturer in statistics, PVKN Government College, Chittoor. In this video lecture, we are going to discuss mathematical expectation, variance, covariance, theorems on mathematical expectation, and properties of expectation. This is our learning objective: introduction to mathematical expectation, definition of expectation, variance and covariance, addition and multiplication theorems on expectations, and properties of expectation, variance, and covariance. Let us introduce the concept mathematical expectation. We already know the distribution function capital F of x or density function small f of x and probability mass function p of x or give us information about the random variable. We need more description of the variable, such as a single number which describes the entire function or entire data. One of such number which represent the whole data in a single number is nothing but mean, and this is expectation of x. The terms expectation, expected value, average value, and mean value are all used for the same concept. The expected value is used as a measure of centering or location of a probability distribution. It is an important idea in the study of probability distributions. While studying the probability distributions, we use mathematical expectation everywhere. Let us define the mathematical expectation. If x is a random variable, assuming values x1, x2, xn with probabilities p1, p2, pn respectively, such that summation pi1 is equal to n. Here we have assumed the values up to n and finite data only. Summation I is equal to 1 to n, pi, that is total probability, equal to 1. Then the mathematical expectation of x is defined as some expectation of x is equal to summation I is equal to 1 to n xi into pi. We multiply the corresponding variable value into corresponding probability value, and we add all these multiple products, we get the expected value of x. Also, if the random variable x takes infinite number of values I is equal to 1, 2, 3, so on, then expectation of x is defined as I is equal to 1 to infinity xi pi, where total probability is equal to 1 provided that the series is absolutely convergent. That is, if expectation of x is equal to I is equal to 1 to infinity modulus of pi xi, that is equal to modulus of pi xi into modulus of xi is less than infinity. Let us define the mathematical expectation in case of continuous random variable. In case of continuous random variable, the probability density function is f of x. Then the mathematical expectation is equal to minus infinity to plus infinity x into f of x dx. Provided minus infinity to infinity modulus of x f of x dx is less than infinity. Expectation of a function of random variable. Let g of x is the function of a random variable, then expected value of g of x is defined as usual, in place of x we have function of x, g of x. Expectation of g of x is equal to summation infinity g of x into probability of x for discrete random variable. For in case of continuous random variable, integral g of x f of x dx for f x is continuous random variable. Let us define the variance and moments. If x is a random variable, then its variance is given by variance of x is equal to expectation of x minus expectation of x whole square. This is equal to expectation of x square minus expectation of x whole square. That is equal to, we denote it, variance is mu2. Here, simply applying the a minus b whole square formula. In case of a, in place of a, x we have, in place of b, expectation of x. This is x square a square plus b square minus 2ab. This is equal to, we take expectation inside. Expectation of x square plus expectation of x whole square, this is a square, this is b square, minus 2 into expectation of x gives expectation of x into expectation of x. This is equal to expectation of x plus 1 expectation of x square minus 2 expectation of x whole square. This minus 2 plus 1 gives us minus 1 expectation of x whole square. For a discrete random variable, variance is defined as expectation of x minus expectation of x whole square. This is equal to summation x into x minus x bar whole square into p of x. Similarly, for continuous random variable, mu2 is equal to minus infinity to plus infinity x minus x bar whole square into f of x dx. We define expectation of x as first raw moment mu1 dash. Mu1 dash is nothing but expectation of x. Non-central moments of rth, non-central moment or rth moment of origin is expectation of x minus about origin means 0. This is equal to nothing but expectation of x power r. Here, in this case, we define expectation of x is equal to summation x power r into p of x. Or in case of continuous random variable, integral minus infinity to plus infinity x power r f of x dx. About any arbitrary point a, the expectation of x is defined as x minus expectation of x minus a power r. The central moment or rth moment about mean is nothing but expectation of x minus expectation of x power r. Let us define the last concept, covariance. If x and y are two random variables, then covariance between the variables x and y is defined as covariance of x is equal to expectation of x minus expectation of x into y minus expectation of y. This formula can also be expressed as simply multiplication x into y, x into expectation of y, expectation of x into y, expectation of x into expectation of y. This minus 1 minus minus gets become plus 1. Here, taking expectation inside, expectation of xy, expectation of x into expectation of y. Since we apply expectation of on a random variable, it becomes a constant. Expectation of constant is nothing but constant itself. Expectation does not work again on an expectation. So this expectation does not work on expectation of y. So expectation of x into expectation of y minus expectation of y into expectation of x plus expectation does not work. So this term becomes here. Here we have this minus this plus gets cancelled, and expectation of xy minus expectation of x into expectation of y. So covariance of x is equal to expectation of xy minus expectation of x into expectation of y. With this view, we define independence of random variables using expectation. Random variables x and y are said to be independent if expectation of xy is equal to expectation of x into expectation of y. If x and y are independent, then covariance of xy is equal to expectation of xy minus expectation of x into expectation of y. Since expectation of xy is equal to expectation of x into expectation of y, this plus and this minus gets cancelled. This becomes 0. So for two independent random variables, the covariance between them is 0. Next important theorem, addition theorem on mathematical expectations. The statement is the mathematical expectation of sum of two random variables is the sum of their individual expectations. Symbolically, if x and y are two random variables, then expectation of x plus expectation of x plus y is equal to expectation of x plus expectation of y. Let x and y are two continuous random variables. Let us prove the theorem. Let x and y be two continuous random variables with joint probability density function f of xy and marginal probability functions f of x and f of y respectively. By the definition of expectation, we have expectation of x is equal to integral minus infinity to plus infinity x into f of x, since we consider two continuous random variables. So expectation of y is equal to minus infinity to plus infinity y into f of y dy. Now consider, by definition, expectation of x plus y is equal to minus infinity to plus infinity minus infinity to plus infinity. In place of x, we have x plus y f of x y dx dy. Since this is joint random variable, we define expectation of x plus y like this. Simple multiplication, x into f of x y dy took here, x into f of x y dy plus y into f of x y dy. I just keep the bracket here. This x comes here, bracket minus infinity to plus infinity f of xy dy here. By using the commutative property, we can write like this. Okay, here also y here f of xy into dx. This is nothing but this function integral minus infinity to plus infinity f of xy dy is nothing but marginal of f of x. This is marginal of f of y. Okay, this is marginal density function of f of x. This is marginal density function of f of y. So this becomes integral minus infinity to plus infinity x f of x dx. This is y f of y dy. This is equal to expectation of x plus expectation of y. Here f of y. This is f of y. If x and y are two random variables, then this is multiplication theorem on expectations. Expectation of xy is equal to expectation of x into expectation of y. Let x and y be independent continuous random variables. Then by the definition of expectations, we know that this is the expectation of x and expectation of y, where f of x and y are marginal probability density functions of x and y. Also, expectation of xy is equal to xy into f of xy dx dy. F of xy is joint probability density functions. Since f of xy are independent, we can write f of xy is equal to f of x into f of y, since x and y are independent. Simply, by using commutative property, minus infinity into infinity x f of x minus infinity to infinity y f of y, nothing but expectation of x into expectation of y. We just proved the addition theorem and multiplication theorem for two events. We can generalize these theorems for n events also. Okay, next concept is properties of expectations. The first property is expectation of c is equal to c itself, where c is the constant. Let us prove the property. By definition of expectation, expectation of c is equal to minus infinity to plus infinity c into f of x dx. This is nothing but c comes outside minus infinity to infinity f of x dx. This is equal to 1. C into 1, this is equal to 1, because this is nothing but total probability. Total probability always is equal to 1. So expectation of constant is constant itself. Similarly, expectation of 0 is equal to 0 itself. Expectation of 1 is equal to 1. Second property is expectation of ax is equal to a into expectation of x, where a is a constant. Let us prove this. By definition of expectation of ax, minus infinity to plus infinity. In place of x we have ax into f of x dx. A comes out minus infinity to plus infinity f of x dx. This is nothing but here x into f of x dx. This is equal to a into expectation of x. Here we need to keep x. Similarly, expectation of ax plus by is equal to a into expectation of x plus b into expectation of y, where a and b are constant, x and y are two random variables. Let us prove this. By definition of expectation of x, we have expectation of ax plus by is equal to double integration ax plus by. In place of x we have ax plus by f of xy dx dy. Here f of xy is the joint probability density function. We have simply separating ax into f of xy dy dx dy, by into f of xy dx dy. Simply, you remember the addition theorem on mathematical expectations. A comes out minus infinity to plus infinity x into, I just separated minus infinity to plus infinity f of xy, x here, dy, here dx. This is nothing but marginal density of x and this is nothing but marginal density of y. Okay, this is equal to, again, this is expectation of x and this is expectation of y. So a into expectation of x plus b into expectation of y. Hence the theorem. If x is the random variable and a is the constant, then expectation of a into psi of x is equal to a into expectation of psi of x, and expectation of psi of x plus a is equal to expectation of psi of x plus a. We can prove this by using mathematical expectation. In place of x we have a into psi of x, a into psi of x f of x dx. A comes out minus infinity plus infinity psi of x into f of x dy. In place of x we have psi of x, so this is expectation of psi of x. Similarly, expectation of psi of x plus a is equal to, by definition of expectation of x, in place of x we have psi of x plus a, so simply this multiplies two terms, psi of x f of x dx, a into minus infinity plus infinity f of x dx. This is equal to, this is total probability becomes 1. This is psi of x, expectation of psi of x plus a. If x greater than or equal to 0, then expectation of x is greater than or equal to 0. If x is a continuous random variable, we have x greater than or equal to 0, then by definition of expectation of x minus infinity to plus infinity x f of x dx. Since the probability function is always positive and we assumed that x is greater than or equal to 0, this becomes 0 to infinity x f of x dx. This, there is no negative term in this integral, so this becomes greater than or equal to 0. If x and y are two random variables, if x is less than or equal to y, then expectation of x also less than or equal to y. Since x is less than or equal to y, we can write this as y becomes here, y comes here, minus y less than or equal to 0. Taking expectations on both sides, expectation of xy less than or equal to 0. Simply apply expectation of x minus expectation of y less than or equal to 0. This becomes expectation of x comes right hand side, expectation of x is less than or equal to expectation of y. Let us look at the properties of variance. Variance of c is equal to 0, where c is a constant. Variance of constant is 0. So by definition of variance, variance of x is equal to expectation of x minus expectation of x whole square. In place of x we have c, expectation of c minus expectation of c whole square. This is expectation of c minus c becomes 0. Since this expectation of c is equal to c, so variance of constant is 0 always. Variance of a into x is equal to a square into variance of x. By definition of variance, we have In place of x, we have ax. Expectation of ax minus expectation of ax whole square. Simply, this a comes here. We know that expectation of ax is equal to a into expectation of x. So, common a here, x minus expectation of x. And this a square comes out. This a square, this is x square. This a square comes out, a square into expectation of x minus expectation of x. This is nothing but variance of x. So, expectation of ax is equal to a square into variance of x. Variance of ax plus b is equal to a square into variance of x, where a and b are constants. By definition of variance, we have in place of x, we have ax plus b. Variance of ax plus b is equal to expectation of ax plus b minus expectation of ax plus b whole square. Here ax plus b, this ax taking expectation inside, a into expectation of x minus b into expectation of b becomes b. We know that expectation of constant is equal to constant itself. Here this plus b minus b gets cancelled. Common ax minus expectation of x whole square. This a comes out and this a comes out becomes a square. A square into variance of x. Variance of ax plus b is equal to a square into variance of x plus b square into variance of y plus 2ab into covariance of xy, where a and b are constants. By definition of variance, variance of ax plus b is equal to expectation of ax plus by minus expectation of ax plus by. This is in place of x we have ax plus by. This is x and also this is x. Simple transformation inside the bracket ax plus by. This becomes a into expectation of x plus b into expectation of y. This is a into expectation of x, b into expectation of y. Common a x minus expectation of x plus b by, this by, this is minus here, plus into minus, minus, okay, b common, expectation of y remains. So a, this is a and this is b, a plus b whole square. This is a square and this second term becomes b square. This is 2ab into a into b. Put a is equal to x minus expectation of x, b is equal to y minus expectation of y. Okay, you imagine this is a square plus b square minus plus 2ab, a plus b whole square. Now this is nothing but a variance of x, this is nothing but variance of y. This is by definition of covariance, this is covariance of x and y. Properties of variance. Similarly, we can show that in place of minus, here minus comes. Variance is independent of change of origin but not scale. This is an important property. Let us look at the proof. Let u is equal to x minus a by h, where a indicates change in the origin, h indicates change in scale. U is equal to x minus a by h. This h multiplies here. UH is equal to x minus a, and a is equal, x is equal to a plus UH. Taking expectations on both sides for this term. Variance of x is equal to variance of a plus HU. This is equal to, by definition of variance, expectation of a plus HU minus expectation of a plus HU whole square. A plus HU, taking expectation inside, taking expectation inside, this is equal to expectation of A HU minus expectation of A is equal to A itself minus H into expectation of U. This is equal to expectation of common H. This plus A minus A gets cancelled. Common H U minus expectation of U whole square. Nothing but this H square comes outside. H square into expectation of U minus expectation of U. This is equal to H square into this is variance of U. So variance of X becomes H square into variance of U. Properties of covariance. Covariance of Ax, By is equal to AB into covariance of X, Y. By definition of covariance, we have covariance of xy is equal to expectation of x minus expectation of x into y minus expectation of y. So, covariance of ax plus by is equal to expectation of ax minus expectation of ax, by minus expectation of by. This is equal to ax, common a here, a into x minus expectation of x, b into expectation of y. AB comes out and expectation of x into expectation of y, y minus expectation of y, this is equal to AB into covariance of xy. Covariance of x plus a, y plus b is equal to covariance of xy. By definition of covariance, we have covariance of x plus a, y plus b. This is equal to expectation of, in place of x, we have x plus a. Okay. Simple algebraic transformations inside the flower brackets. X minus a, expectation of x minus expectation of a is equal to minus a. Here also y plus b minus expectation of y minus b. This is equal to this plus b plus a minus a gets cancelled. Expectation of x minus expectation of x, y minus expectation of y, nothing but covariance. This is equal to covariance of x plus y. So the origin does not influencing covariance. So covariance is independent of change of origin. Here this covariance is dependent on scale. Covariance of ax plus b, cy plus d is equal to ac into covariance of xy. By definition of covariance, we have expectation of ax plus b minus expectation of ax plus b plus cy plus d minus cy plus d. Simple algebraic transformation inside, this becomes plus b minus b plus d minus d gets cancelled. This remains, we have. This is expectation of a into expectation of x plus expectation of x, c into y minus expectation of y. And this ac also comes outside, ac into covariance of xy. Next property is covariance of ax plus by, cx plus dy is equal to ac into variance of x, bd into variance of y, plus ad plus bc into covariance of xy. By definition of covariance, we have covariance of ax plus by, cx plus dy is equal to, this is in place of x we have ax plus by, in place of y we have ax plus cx plus dy. Common a, this remains x minus expectation of x. Common b, y minus expectation of y remains. Here also common c, c into x minus expectation of x, d into y minus expectation of y. This is this up to this a and up to this b. We have simple multiplication. A into c, ac into x minus expectation of x into x minus expectation of x, x minus expectation of x whole square. Here x minus expectation of x into c, x minus expectation of x. Okay, this is a into c, this is b into c, this term. Okay, this is become product terms, and we have two square terms, two product terms remains. expectation of y minus expectation of y. First AC, BC. Similarly, AD, BD. Okay. This is nothing but variance of x. This is covariance of xy, and this is covariance of xy AD into BD into variance of y. Common covariance of xy AD plus BC. AD plus BC. AC into variance of x, BD into variance of y, AD plus BC into covariance of xy. Covariance is independent of change of origin but not scale. Let u is equal to x minus a by h, v is equal to y minus b, ab indicates change in origin, hk indicates change in scale. We have x is equal to a plus uh, y is equal to b plus vk. Consider covariance between x and y. Substitute in place of x we have a plus uh, in place of y we have b plus vk. By simplification we can get covariance of xy is equal to hk into covariance of uv. So covariance is independent of origin, dependent on scale. Let us conclude the lecture. We have introduced the concept mathematical expectation, definition of expectation, variance and covariance definitions with addition and multiplication theorems on expectation. Also, we have discussed several properties of expectation, variance and covariance. Thank you.